All right, let's finish up this chapter. And so like we had kind of mentioned Monday, we're kind of seeing that maybe we can have different number of substituents attached to the same atom. Trying to pull up our xenon. Where did xenon go? So even in the case of xenon, right, we had xenon difluoride and xenon tetrafluoride. And so that brings us to naming. And so again, this is the difference between these covalent compounds versus the ionic compounds. So now with the molecular, or again, we can use the term covalent compounds, we can't just determine the formula, right, because they don't have set oxidation states like we saw with our ionic compounds. And so nitrogen and oxygen are really good examples of this. And so oftentimes, like if you see a discussion about pollution and like these NO gases, they're often abbreviated as NXOY. And so this is why, because there are so many different combinations. If you're talking about NO gases in the environment, you can actually be referring to the whole kind of family of them. And so then to name them, so first we just name our prefix, and then if there's only one atom of the first element, we omit the mono. And then we have our first element name, and then prefix, again, right, indicating how many. And then we change the ending of our second element to "ide." So now we can kind of practice with these, right? So NO is nitrogen monoxide. NO2, so nitrogen dioxide. N2O, now dinitrogen, since that one, right, was the first one that deviated from 1. So now we do need a prefix, so dinitrogen, and then monoxide. And so we can keep going. Let's finish out these. So N2O3, dinitrogen trioxide. So N2O4, again, not dinitrogen tetraoxide. And finally, the last one on this list, so N2O5, once again, dinitrogen, and now pentaoxide. And so I'm not the greatest speller, so I may have misspelled some of these, and I'll be, again, lenient on your spelling. All we mainly care about is the correct prefixes, and then hopefully I can interpret the rest of the name, but just give it your best shot with spelling. So that's kind of, I think that's relatively simple. So again, we just have to keep in mind our prefixes, which should be somewhat familiar. All right, so look at these for practice. So take a few minutes and come up with the names, and then we'll go over them. let's hear what we have. So what do we get for A? Yeah, perfect. So nitrogen, and I believe that one has 2 I's, but again, I'm not the greatest speller, so triiodide, good. What about B? What's that one? Phosphorus pentachloride, good. Again, hopefully feels pretty straightforward. If not, do ask questions. And then this last one, C.
Tetraphosphorus decasulfide.
Perfect. Tetraphosphorus decasulfide. Excellent. Questions on those? And then, right, so for our purposes, we're only going to be naming these like binary complexes, right, with 2 different molecules. Obviously, covalent compounds can get pretty complex. We could go into drugs and blah, blah, blah. And everything has special names and stuff. So that's more for OCHEM. All right, so other things that we should cover is, well, how do we determine our formula mass? And this may be, again, kind of self-explanatory, but let's go over it. And so it goes back to kind of what is on the periodic table. And so it's kind of convenient. So they don't really have units on here. And that's because it depends what you're talking about. So, right, this could be the average atomic mass, and this could be given in AMU, right? So that's, again, atomic mass units. So going back to our notes, so we could be talking about a single molecule. So that's where we would be in these AMU units. And you just get the numbers from the periodic table, if that wasn't apparent. And so going back, so let's practice this one together. So of course, water, again, just get the numbers from the periodic table. And then yes, there can be small discrepancies. I don't mind, right? We'll have slightly different answers with rounding. So this one reports it to 1.008 for the mass of hydrogen. Some people will just round to 1. You know, this one rounded to 1.01. So again, right, slight variations. Same thing with the mass of oxygen. They chose 16. You could have plugged in 15.999. So that's fine, right? Numbers will slightly vary. And then you just add them together. And so, of course, following the formula, so H2O, so we have to multiply our mass of hydrogen by 2 since there's 2. And so that's how we get 18. But then part of how it's set up and why, we'll get to Avogadro's number later, but kind of how it works out is, well, not only is this mass an AMU, but it could also work out that we could be talking about grams per mole. So if we're talking about a mole of substance, we're saying that 1 mole of carbon is 12 grams. And so mole is just a special unit in chemistry. And so this is its molecular mass, again in grams for a mole. And so not only does one individual water molecule weigh 18 AMU, but we can say 1 mole of water is 18.02 grams. Or, 18 whatever. So whatever you round it to. Not too bad. Let's try an example. So let's just find the molecular weight of silicon tetrachloride. So just add it up, do a little practice, make sure we're all on the same page. All right, so what do we get? And again, we can go through this together. So silicon, again, right, you can take your own liberties with rounding, or if you're looking at a different resource. So 28.086 plus, and then we had 4 chlorine, so 4 times 35.453, or you could have rounded it to 45. And so then, again, depending on rounding, you get 169. And then just try to keep track of the sig figs right amongst yourself. So I've bothered to put all 5, so then I should report this to 5, right? 169.90. So just try to be consistent with yourself, with at least the sig figs, but I likely won't be watching for sig figs right on like molecular weight calculations. It's more of in-lab values. All right, so then that ends up rounding up, and again, that's 169.9 grams per mole. So do we all get that? Sound okay? Any questions? All right, so let's look, we just want to look at molecular geometry again. And so we're mainly just kind of trying to hit the highlights of these. And so let's look at some classic examples of trigonal planar. And so like I mentioned, these first examples might be a little strange. And so we have kind of boron, trichloride. And again, this is where maybe the electronegativities give us a better indication that this is a covalent compound. Otherwise, right, you might have assumed that it's an ionic potentially, although boron's kind of right on the other side of the stair step. But that group 3, right, is a little weird. And so yes, they tend to still make covalent compounds, so this had to be proven by crystal structure. And then other odd things about this structure, of course. So what else is odd about it? I'll let you answer that. So think back to Monday, right? What usually has to be true for these structures? Yes. So it does violate the octet rule, and that is actually okay for group 3. So only 6 electrons, right, that it feels. That's okay. So again, right, it's this trigonal planar structure, so it's flat. And as you might imagine, so that's also why these group 3 elements are interesting and reactive. So aluminum is similar. And again, all these tend to be like angry fuming liquids. So boron trichloride is an angry fuming liquid. Aluminum trichloride is an angry fuming powder. And then people like using boron because it does this weird thing of like, yes, it can have 6 electrons, and then I'll try to get 8. And so that makes it interesting reactivity-wise. And so again, 3 things attached to it. Trigonal planar. And now would be a good time. We could also look up the compound chem sheet that I gave out on Monday. So again, just orienting ourselves. So we're at 3 electron pairs, right? Just 3 things attached to it. So this first one, 3 bonding pairs. And then it tells us, yes, the geometry is trigonal planar. And then you can note, of course, right, there be all even angles, so 360 divided by 3, so 120 on all those angles there.
Is there any difference between the bent and the trigonal plane? How to differentiate?
Between these
ask
two?
us?
So then a bent one for that one. So there's actually 2 bents. So see if you can draw out SO2. So draw out that structure. And then, so ideally, the best structure, and again, you don't have to get there right away, right? So you could be playing with some single bonds, but then you'll be fighting with those formal charges and trying to get octet satisfied. So of course, sulfur is hypervalent here, so that's okay, right? You could probably draw another resonance structure where it's not hypervalent, it will just have formal charges. So that's why this structure is kind of better. So no formal charges. But then this, so let's compare that to what we were looking at. So back to this chart, right? So trigonal planar has 3 substituents. And then this is actually a special bent here. So this is one variation of bent where we have 1 lone pair and then 2 things attached. And so SO2 is that classic example And so this chart doesn't make that distinction, and I won't make you make that distinction, but sometimes this is also called V-shaped vent. So you might see that. Like I said, I won't ask you that specifically in this class. This is just kind of an aside if it comes up. Yeah.
And how do you know that the sulfur dioxide is supposed to be V-shaped vent and not linear?
Because of the lone pair.
Okay.
So that's where the Vesper chart is handy. Because remember, the lone pair still occupies space. So that's why they're treated as electron pairs, right? So write that as a reminder if you need it, that this is both lone pairs and atoms. So how many things are on it? So yeah, this is our guide here. So if it had no lone pairs, it would be linear. And then there are other variations too, like the xenon difluoride, right? It could be linear, but it has 3 lone pairs. It's just, we won't get into all the depths of geometry in this class. So we're just trying to point out kind of the classic examples. All right, so with that, let's look at the classic example of tetrahedral. So what's our classic tetrahedral structure or molecule? There's one super classic one, and then there's another one that we did that comes up a lot. Carbon, what was it? C, or carbon something. Yeah, so CH4, so methane, so, or you could have been going for like carbon tetrachloride, tetrabromide, any one of those families. So yeah, methane is, like I said, always the classic example, so we went over that. So again, just kind of practice drawing that. I forgot my Molly Mont kit again, that's what I forgot. And so if you didn't play with those Molly Mods in class, right, it would always be, you can always ask for them, borrow them. So again, right, they have their tetrahedral structure, so we can go back to this chart. So tetrahedral, 4 things attached to it. And so other ones, so remember ammonium is kind of the other somewhat classic example, right? We had ammonium salts today in class too, so that comes up. And then, yeah, I'll put kind of those on there in case they were kind of on the tip of your tongue with the carbon with 4 things to it, or anything in group 4 with 4 things to it. All right, so tetrahedral, again, know that shape. And then trigonal pyramidal, again, you want to understand that it's essentially a variation of tetrahedral, and we just replace one of these substituents now with a lone pair. And so do you remember what the classic example for trigonal pyramidal?
Nitrogen trichloride?
Yeah, so nitrogen trichloride is a good one, or ammonia. So that's kind of the classic. But yeah, you got the right idea. So group 5, 3 things attached to it. Again, you're thinking about that lone pair on nitrogen for these. All right, keeping the geometry simple in this class too. Kind of messed up my stereochemistry, but that's okay. And again, right, you can appreciate that it's a variation from this Vesper chart. So again, instead of 4 bonding pairs, we have 3 bonding pairs in 1 lone pair. And then, again, appreciate the slight distortion. I'm not going to be testing you in all the little angles, but you can still appreciate how the lone pairs occupy some more space. and thus push these tighter. All right, and then back to bent. So we did sulfur dioxide, which like I mentioned was this kind of special V-shaped bent. But then what's our other bent example? That's our very common molecule. Water. So yeah, water is the other bent. And the distinction is this one has 2 lone pairs. So truly this one is a modification of tetrahedral. So we could even say if there's a term electron geometry, so that just means like electronically, right? They have the same orbitals. So tetrahedral electron geometry, and that's clearer from here. So right, still 4 electron pairs, 2 bonding pairs, oops, sorry, and now 2 lone pairs. So that creates this different angles. So again, right, you could, if you really wanted to get into it, you could compare, right, these 2 bent angles. So again, the SO2 one is larger at 119 versus the water one. So it's always 104.5 for the water, so that's classic. But again, in this class, we'll just call them both bent here.
What about the hydronium ion?
So the hydronium ion would take another geometry.
Will it still be tetrahedral?
Well, I mean, so let's, I mean, I wouldn't ask you. Because hydronium, yeah, I think it'd be well, it'd be trigonal planar technically, but that's kind of on the side right now, right? So the hydronium picks up water, so then it makes, or picks up a hydrogen. So this would technically be hydronium, so yeah, it'd be a trigonal pyramidal, but yeah, I won't quiz you over like weird stuff like that. We'll try to just stick to the major examples. So let's look at polarity now. And so polar molecules, we kind of need 2 things for a polar molecule. So first of all, for polar molecules, we need to have some sort of difference in polarity. And so usually this involves, you know, electronegative elements, so oxygen or chlorine, sulfur, etc., right, anything that's electronegative. But then it also has to have asymmetry. And so let's look at that, and we'll look at some, like I said, some examples. And so first let's look at some nonpolar compounds. So of course, methane is nonpolar. So not only, right, these bonds themselves are not really polar, so CH bonds are pretty normal. So that is nonpolar, and then it's all the same in every direction. And so we'll understand that more in a bit. So now let's look at carbon tetrachloride again. So we had mentioned this compound on Monday, that this was a great NMR solvent. And so this molecule, we can have individual bonds that are polar, right? So this bond itself is probably polar. We could calculate the electronegativity if we wanted. So we can look at it. So 3.16 minus 2.55, oops. And so, right, it's just over 0.4, so technically polar. But if we look at the structure itself, and so the way to think about it, So there's a few different ways to think about it. And so if you want to think about it like the mathematical way first, is you want to draw what's called your vectors. And chemistry is opposite from physics in that we draw this little arrow towards the more electronegative element. And then I like to put a little tail on there so I remember which one's positive. And if we do this, though, we would find that all our vectors cancel out. So again, even though every bond is polar individually, this whole molecule, right, is nonpolar overall, since it all cancels out. Now, that's maybe not the most intuitive thing to see. So what I always tell people to, as our hint, is write everything in this first column is going to be your fully symmetric molecule, right? So as long as all these atoms are the same or relatively the same, then it would be nonpolar. And so now let's look at another example where that's not the case. And again, you'll kind of see what I mean. And so now this is polar. And this molecule is dichloromethane. And so if we look at this, right, again, there's different ways to analyze it. So we could think about who's electronegative. Well, our chlorines are. So if we just draw kind of our vector analysis even, and we kind of see, well, you know, it's maybe just on one side of the molecule that's pulling this electron density towards it. But then you can also see, okay, well, it's still tetrahedral, but since I've broken the symmetry, right, by having chlorines and hydrogens, it's no longer symmetrical. So as long as you've broken the symmetry, it's polar. And so that means, right, chloroform is also the same. So, right, we could replace one of the hydrogens, or just have one chlorine, I mean. And, right, still polar. You could have 3 chlorines, right? Still polar, as long as there's some sort of unevenness. So that's what you're looking for. And so again, right, that can apply to other molecules. So just thinking back to sulfur hexafluoride, right? Again, this is another good example of we have a bunch of electronegative fluorines, but then sulfur hexafluoride itself, again, is going to be nonpolar.
Subtract the 2 elements only, not the sulfur minus the 6 fluoride in it.
No, just, yeah, you just compare like the bond, right? So the two, so the difference between sulfur and fluorine. And again, that's just kind of like a guide too. You don't even necessarily have to do that. You can usually just judge by electronegativity. So like if you see hydrogens, it's usually nonpolar. But if you see like halogens, you're thinking, could it be polar? And that's where you're looking for the symmetry.
This one of the chlorine and the hydrogen, please kind of like repeat them.
So this one?
Yeah.
So this one, right, we have a chlorine there. So we've broken the symmetry, right? So we have 3 hydrogens, but then the chlorine is still pulling in this direction. So that makes it polar.
Okay, we don't calculate the electronegativity.
I mean, I just didn't because we had kind of done it previously. But again, since it's a halogen, you know it's already going to be electronegative. So other kind of examples. Oh, well, let's just clarify. So, right, water is obviously polar. That's not clear, right? So it has those lone pairs. So you're also looking for like lone pairs too. So again, high region of electron density. And it again breaks our symmetry, right? Going back to the Vesper chart, well, it's not in the fully symmetric category, right? It's over here, so it's polar. So basically anything that's not this geometry is probably polar, right? So like ammonia is polar because it has a lone pair. Water is polar because it has a lone pair. So we could put that down, right? So ammonia, just to be explicit. So that is polar, right? From the lone pair. Same thing with water, so polar. And we'll also get into hydrogen bonding later, but we have this hydrogen bond, but we haven't quite defined that. And so let's just look at other kind of groups. And so again, kind of looking for asymmetry. So any like carbon double bond to oxygen, right? This is also generally polar, just because again, if you have, let me give a more explicit example, like acetone. So this is acetone, but again, ours, you could have any carbon chains or whatever. And so acetone is polar since, right, these are considered nonpolar, so these are just carbon-carbons. In case I wasn't clear, so CH3, right, don't forget these little points. And so we do have oxygen though, so electronegative, so it is pulling in that direction. So yes, that would be polar. And then this is perhaps a little beyond where we are at the course, but I still like mentioning this. So if we look up any compound, and I like going to Wikipedia here. So we have acetone, so right, it gives us a nice picture. We always have, oops, sorry, our ball and space film model here. So again, just keep the 3D structure. But then if you're ever confused about polarity and you just want to kind of check yourself, there's this thing called the dipole moment. And as long as it's like, basically, if it has a numerical value, and I'll show you ones that are nonpolar so you can see. So then it's polar. So right, acetone 2.88. And then this dipole moment is just like literally something you can measure. So you can actually measure how polar is it. And then, so let's look up carbon tetrachloride. So we look at carbon tetrachloride, scroll down to its dipole moment, and so it's at 0. So right, so that tells you, okay, that's very nonpolar. And so that's just kind of a nice checkpoint. And then let's just look up, might as well look at water's dipole moment, see what something really polar looks like. So dipole moment, and so they can get bigger than this. So I thought waters would be bigger, but so 1.8 there for the dipole moment. So again, that just kind of gives you more references as you're learning. Does that make sense? Feeling okay about that? I'll put in, where'd my pen go? There it is. I was just going to throw in other groups because we could look at, let's look at ether because this one might be slightly polar. So ether, I probably should have chosen diethyl ether. So there's diethyl ether. Again, right, we have oxygen. That's a good indication that something might be polar. So it's got those lone pairs. And again, you can check the dipole moment, so 1.15. And so, right, again, polar there. Questions about polarity? Are you feeling okay? We could try other examples too. So let's just look at other, oh, that's not what I wanted. So I'll just show some more, let's do some more non-polar ones up. There we go. So this is another example of just non-polar. So I just picked a hydrocarbon chain. And so again, right, the other thing you're kind of noticing is anything with just a bunch of CHs is probably going to be non-polar. And so this is called a hydrocarbon. So AKA, right, it's just some sort of CH formula, right? So there's not groups in it. And yeah, that could go into fats too. Trying to pull up an oil picture. There we go, Wikipedia. And so then, right, this is also why fats are considered pretty non-polar. So even though it does have this little group at the end, so this is a carboxylic acid group, right? So this could be considered polar, right? But the main part of your fat is a huge hydrocarbon chain. And so this has actually 9 carbons repeated here, looks like from the formula. So right, these chains are repeated. Actually, it's not very clear what it's trying to say. I think it's just trying to count them for some reason. So 9, 10, yeah. But it's basically this large hydrocarbon chain, so that essentially makes it mainly non-polar. And so that goes into miscibility with water or lack thereof. But we're not quite there in the course. All right, so then the last bit is just examining these structures and seeing if we can write some formulas. So let's practice. So take a few minutes. And my suggestion would be, right, copy it down and then label all your carbons, right, count your carbons. Don't forget that every one of these points is a carbon. Don't forget the hydrogens aren't drawn. All right, let's start to hear answers. And so you can kind of see the sketch work that I did. So again, right, you want to make sure that carbon has 4 bonds, and then any point here, again, is a carbon, and then it has to, again, have 4 bonds, so that's how we know this one has CH3. And then the tricky ones are on this ring, right, so you got to kind of look. So, okay, this one only has 2 bonds, so it has 2 hydrogens, right? This one has 1, 2, 3, so it has 1. And then 1, 2, 3, 4, so don't need to do anything here. Same thing here, 1, 2, 3, 4. So just kind of watch that. And then same thing on the ring. So how many carbons did we get? 21. Do we agree? 22. See, I got 21 as well, but I'm always open to recounting. So I try to label my carbons, that being said. Could have always skipped one. Did other people get 21 or 22, or I could try to look up the answer, but so let's recount 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So I get 21 again, even on the recount. So, Lulu, did you get the same 21? Yeah, you're nodding. Did y'all get 21 or still kind of recounting? Jada, you get 21 or? Okay, sweet. All right, so 21 looks good for carbon. And then how many hydrogens? What do we get? So count, recount, and then make sure you count the ones that are drawn explicitly too. So what do we, any numbers? $31. So I got 30, but what do other people get? 30, 31, something like that? Here, let me try to recount. I still get 30 again. What do we get? So 30. So I think we're getting 30. So double count. And then how many, so the only element that's left is oxygen, so how many oxygens? Yeah, don't overthink it. 2. So yeah, that heteroatoms are always easy. So obviously, right, the carbons and the hydrogens are the pain here. I got 30, even when I double counted.
With the ones that are already written, right?
Yeah, so including those. Because, right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. At least that's what I keep getting. Unless I've skipped one somewhere. All right, let's try this one. This one shouldn't be as difficult. So this is amphetamine. And then again, right, you can methylate it to make methamphetamine. So let's see if we can get a structure, or a formula, excuse me. So just in the interest of time, we'll keep it moving. So this would be like the level of difficulty that I'll try to get on your exam. So it's not, hopefully not as crazy as THC. So how many carbons did we get for amphetamine?
9.
So 9. And then how many hydrogens? I forgot to count them.
13.
So 13, I like the consensus. And then what's our only heteroatom left?
Nitrogen.
So nitrogen, and then don't need to put anything for 1. All right, good. Any questions on that, how to interpret these? So again, just kind of keep practicing. And then the only thing I'll point out too on this one is, right, this hydrogen was probably the trickiest one. So, right, you see this carbon 1, 2, 3, and then just make sure you have that 4th bond there. All right, so let's get ready for the quiz. Again, you're welcome to take a break. If not, you can dive right into it. I would have your polyatomic sheet out. You're probably going to want that to help you. And then otherwise, it's just ionic compound naming, so you can have your notes out for that to help you. Have those notes out for those common ions, right? Which ones are always certain oxidation states.